Swayam Prabha. Digital India. Educated India.
Welcome. So, we are having the last lecture of this module. So, in this lecture I will basically, a small portion is left, actually thermoelastic problem. So, thermoelastic problem means we are here going to discuss uncoupled linear thermoelasticity. This uncoupled linear thermoelasticity means heat conduction is not considered coupled with the stress problem, that is mechanical stress problem, or the thermal stress is not coupled with the mechanical stress. So, that is the main thing. So, the heat conduction equation, you can also use the coupling term here. So, that is coupled thermoelasticity, where the heat conduction as well as the Navier's elasticity equation you can solve in a coupled manner. So, in case of a linear uncoupled thermoelastic problem, what will be the finite element formulation? For instance, if we consider the previous example, let us so in the previous lecture we have done one small example by hand. So, here with the constant strain triangle, the same example if I consider now, and now in this it was I think 120, it was 120 inch I think, and this is probably say 160. So, now this problem was we did this problem for the a small with two element, that means 4 nodes and 6 degrees of freedom. So, what we did is we derived the stiffness matrix, we derived the force vector. So, force was one axial force. Now, I think E was given 30 into 10 to the power 6, and then nu was given as 0.25, and then suppose instead of some axial force in this phase, phase which we did earlier, instead of this force we now apply a constant temperature change. So, that means if there is a heat source in it, and due to that heat source, it can be from outside, it can be from inside also. So, from the heat source the body gets heated up to 50 degree centigrade compared to the ambient temperature or the outside temperature. So, that naturally will create the thermal stress. So, now how to solve that kind of problem? So, we know that in this case that if you look the stress strain curve, so initial, it is essentially an initial thermal stress problem. So, stress strain curve, it will not start from here, rather it will start from here. So, this is the initial part of the thermal strain. So, and this will be standard Young's modulus. So, this is the stress strain curve, one dimensional stress strain curve that you generally see in thermoelasticity. Now, in case of 2D problem, the strain energy density we know the strain energy density for the non-thermal problem where the temperature change is not there. So, so stress strain relation changes now. So, in case of 2D and 3-dimensional elasticity, the strain that is will be your epsilon. If I consider epsilon is a function of displacement, then epsilon minus epsilon t, or the thermal strain, that will be actually your elastic strain, and that will, if I consider this a linear elastic Hooke's law, so linear elastic, so if there is a stiffness matrix which is the constitutive matrix or constitutive tensor D, then this will becomes my stress strain relation. So now you see, we know what is the strain energy for if there is epsilon t, it is 0, that is for this case we know. So for this case the strain energy will also look like this. So integral over the whole domain, and then it will be your again sigma inner product epsilon, or here the elastic strain will be there. So sigma, if I write in this way, sigma is now epsilon u minus epsilon t. So this is my strain energy. So we can, so there will be a half. So if I just substitute this constitutive equation, then it will look like this, that epsilon of u minus epsilon t transpose, or if I write it in tensorial notation, then it is just inner product with fourth order tensor d, and then your epsilon u minus epsilon t. So this will be my strain energy density. Now the weak form or the governing equation, if I do it from here, so our governing equation is now del dot sigma, if I neglect the body force, so then this is equals to 0. So and so there is no, for this problem there is no applied traction or the mechanical force acting on the body, but it may be it may possible that along with the temperature change there is a traction force acting on the body. So in that case your sigma dot n, that is your traction boundary, will have a traction boundary condition. Now another is displacement. At this phase displacement u is 0, u is actually a vector here, u and v. Now so the governing equation, we can modify this governing equation by putting this constitutive relation or the strain stress strain relation. So this can be written as del dot, if I substitute this, so d colon epsilon u minus epsilon d colon epsilon t. So this equals to 0. So if you look carefully, that this is my total strain and this is my thermal strain. So now this thermal strain actually acts as a body force in the body. So that was my main intention, to show that instead of having a mechanical body force like gravity based body force or something else, okay, this thermal stress change will act as a or the thermal increase in temperature obviously will act as a body force on the body. So actually if I now further modify, this is essentially looks like this. So if you see, this will go to right hand side. So that means the thermal strain you must know. Now to know the thermal strain, what we need, basically we need the expansion coefficient. So that is alpha. So alpha, let us consider here, that is some value of alpha, say 1.2 into 10 to the power minus 6 per degree centigrade or any unit. So that we can choose effectively. So now if I do this, and then if I wanted to solve this problem with the same discretization, for instance 1, 2, 3, 4, and then this is element number 1, this is element number 2, and this T, the temperature change, is 50 degrees, say 50 degrees centigrade. Now if I want to solve by finite element method, then again our force vector will be only the compared to the previous problem, previous exercise, so only force vector will change, because stiffness matrix will remain same, and the traction matrix, or the so if I write the equilibrium equation, that is Ke your into your, say, delta E equals to your now force E, and this is capital QE. So this only this quantity will be 0 now, and this quantity will be non-zero, and this quantity will remain same. Now delta will be for each element, we know what is delta. So delta, for instance, delta 1 will be your U1, V1, U2, V2, and U3, V3. So this is my delta 1. So Ke or K1 we have derived earlier. So similarly for element 2 we can derive it, and then because there is no traction force yet, so there is no Neumann condition, so non-zero Neumann condition, so this will be 0 here. Now only thing is we have to estimate this. So now to estimate this, how to estimate this Fe vector here? So for instance, if I consider now Fe vector, if you remember the expression for Fe vector, that is integral 0 to or integral over the domain, that is your B transpose your force vector, that is your say if you have a force vector that is Fx or Fy, so that will be acting as your sorry, the phi transpose, not B transpose, that is phi transpose matrix, and your force vector, that is Fx, Fe of x, and Fe of y. So phi is a matrix of we know 2 by 6. So now this is my dx dy. So multiplied with the thickness. So this was the force vector. Now here the force vector is different actually. So it is not just a force, body force, but rather it's a thermal strain. So from there we have to compute the thermal stress and then convert it to the body force. So if I now consider, say, plane strain problem, if I now consider or plane stress problem, then what will be the my thermal stress? So plane stress problem, if I consider now, then my thermal stress will be simply epsilon T xx, epsilon T yy, and epsilon T xy. So epsilon T xy will be 0 for isotropic case. So naturally we can write this epsilon T xx, epsilon T yy, and 0. Now in case of epsilon thermal strain along x direction is just coefficient of thermal expansion multiplied by the temperature. So alpha into delta T, or the increase in change in temperature, so that is T. So if I now write this, the same, if I assume the same coefficient of thermal expansion in the y direction also, which is for the case of isotropic material, now we can write this thing alpha T, then we can write this 1 1 0. So this is my thermal strain for plane strain. In case of plane stress, and in case of plane strain, this expression is just multiplied by the 1 plus nu. You know the this thing for the constitutive equation for plane strain. So this is for the plane strain. Now once we know the thermal strain, then you also know the thermal stress. So naturally the if you know the thermal stress, then your weak form will again involving this term. So del dot d that is thermal stress. So this term will come. So you know D, you know epsilon T, and then in the weak form you will get the forcing term, which will contain your the B matrix, that is strain displacement matrix, because of the derivative of the weight function. Because you see there is a del dot is there, so that's why derivative of the shape functions will come. So naturally this thermal Fe thermal will look like this. Fe thermal will look like this, that is integral B transpose. Now then your thermal stress, that is D, D matrix will come, and then your epsilon T. So these are all matrices. Epsilon T is a vector. So this will be dx dy. Now for constant strain triangle, this B is constant matrix. So we can just exactly evaluate this equation or this vector. For instance, T, if I write this, so this is constant, D is also constant if I assume, and epsilon T, that is thermal strain, that is also constant if I assume for an element, then this will be a constant vector. So integral will be an area. So TA then B transpose, like we have found out the stiffness matrix. So this will be like this, and then this can be exactly evaluated. So B transpose is, we all know, that is beta 1 0 0 gamma 1 then gamma 1 beta 1 then 0 beta 2 0 0 then gamma 2 then gamma 2 then beta 2 then beta 3 0 0 gamma 3 then gamma 3 then beta 3. So this is transpose, and then you have so this is divided by 1 by 2a. So again a cancelled. So now D will be your if I assume plane stress constitutive relation, then E by 1 minus nu square, then this will be 1 nu 0 0 sorry nu 1 0 0 0 1 minus nu by 2. So this is my D matrix, and then comes into the thermal strain, that is alpha T, then it will be 1 0 1 1 0. So 1 1 0. So this will be my plane strain plane stress case. So now if I multiply this, then I can easily write this E T alpha capital T, then 1 minus nu square, 2 will be there. So let me write the B transpose it's again. So and then multiply this with this. So this will lead to 1 plus nu 0, right? So this will again give me 1 plus nu common. So now E T alpha capital T by 2 into 1 minus nu, then you have B transpose, then you have 1 1 0. So now if this is the case, then if I multiply this with this 1 1 0, so this vector will come only, so in the first row. So E T alpha capital T 2 into 1 minus nu, then this vector will come like beta 1, then gamma 1, beta 2, gamma 2, then beta 3, gamma 3. So this will be my 6 cross 1 vector. So this is my Fe thermal. So Fe thermal component. So remember that thermal component is not just given as if a body force term. So it is given as thermal strain. From that thermal strain you compute thermal stress, and then you convert it to the body force. And since this is the thermal stress is given actually del dot quantity, so derivative of the stress, so like the normal stress, so your derivative of the shape functions will come into picture. So that's why it looks like this. Now in case of plane strain, you have you know the constitutive equation and you know the thermal strain. So thermal strain also, this is the same with just 1 plus nu multiplied, and in case of plane strain, the thermal the constitutive relation is E into 1 plus nu 1 minus 2 nu, and then it will be your 1 minus nu 1 minus nu 1 minus nu by 2. So this is similar to the plane. So this is your plane strain constitutive relation. Now once this is done, then you can also evaluate the plane strain thermal force vector. So the in this problem, essentially you know to evaluate the thermal force vector, you know alpha, you know T, you know E, you know nu. So once you know these quantities, then beta 1, beta 2, beta 1, gamma 1, beta 2, gamma 2, beta 3, gamma 3, all these quantities also you know, because these quantities are essentially your coming from the shape functions, linear or the linear triangle or the constant triangle, constant strain triangle. So this quantity you can evaluate for each element. So once you evaluate for each element, you can naturally compute for all element, and then you have to assemble as usual and then solve the problem. And once you solve the problem, you will get the displacement due to this temperature rise. Once you know this displacement, then you can compute the thermal stress or the stresses which through this equation, that is stress strain relation. So from here you know epsilon u, so epsilon u will be constant for this element, and then epsilon t also you know, because you know alpha, you know T, and then you know D, so you compute the sigma from here. So this is what the overall thermoelastic problem. Now so this problem can be instead of triangular element, you can apply it with the 4-noded element or the 3D element that you will just introduce 3D element. So those any element can be used for this kind of solution. So this was it. So now I stop